Hello, another video and another model. This time I've been playing with more of a process chart, a flow chart of the COVID situation. And what's prompted this is that I've seen a number of podcasts, a number of video clips where people are using some of the numbers, some of the ratios of confirmed cases to tests and things like that, and extrapolating them up as to guesses of the level of infection or the level of exposure in the population. And some of them I don't think are doing it quite right. And I was trying to find a way of understanding exactly why I thought it wasn't quite right, but also maybe creating a tool that allows me to then explain that. Now, that's what I've done. I may have got myself completely tied in a knot. So I'm creating this video and I hope somebody will watch it and maybe critique, let me know what they think. But bear with me. Let me describe this process flow chart. It's quite, once I've created the whole chart, there's quite a bit in it. But I think it's been quite insightful for me anyway in understanding where the numbers are coming from. And it's a chart that probably is slightly different for each country. So I'm going to talk about the UK situation. But it's something that might be applicable elsewhere and might change in the UK, because if our testing, as indeed it is over the last few days, and perhaps I'll mention that at the end of this little presentation, will change some of the dynamics of this chart. But I'm going to start with this process flow chart, starting on the left side of the diagram. I want to imagine I've got this box that represents box 1, which represents the entire population of the UK. And imagine that's the starting point of this process way back in January or Christmas at the end of last year. And then because of COVID-19, people in that population can have gone one of two directions. You've either been exposed to the virus or you haven't. So what I've done here, I'm creating my flow chart, and I'll put up the little sort of description of what the symbols mean. I've got this transition from box 1 to box 2. So people in the population who've been exposed to the SARS-2 virus, will have moved to box 2. People who've not been exposed move down to box 11, the green box at the bottom of the chart. I've got my cursor here so I can circle that. And I've drawn an arrow between each of those, and I've attached something to each arrow. For this one here, between box 1 and box 2, is the probability of being exposed. The arrow between box 1 and box 11 is the probability of not being exposed. Now, the beauty of that, because they're the only two ways you can exit box 1 on my diagram, the sum of the probability of being exposed and the probability of not being exposed is 1. You must go in one of those directions. Either you have been exposed or you haven't. So the sum of those two probabilities is 1. And that's what I convey at the bottom. Ignore that bottom line there. That doesn't become relevant for the chart I'm going to show you on this one particularly. So once you've been exposed, there's two routes you can go there. Well, actually, what I'll say is the green box in some way represents you've sort of dropped out of the process, because until you've been exposed, you're not going to go any further in this flow chart. So if you end up in the green unexposed box and that's where you stay, that is indeed where you're going to stay. If you're in box 2, though, if you've been exposed, you've got one of two possible destinations. You either develop the infection or you don't develop the infection. So if you end up in box 3 or you arrive in box 3, you have been infected. If you arrive in box 12, you've been exposed, but you are uninfected from that exposure. So we've got two more probabilities: probability of being infected once exposed, and the probability, although exposed, not infected. So there's our two probabilities there. Again, because they're the only possible routes out of box 2, the sum of those is going to be 1. And the probability here, probability infected, you've been exposed, what's the probability of being infected, is in a measure the susceptibility of the person. It's a measure of susceptibility to the virus. Let's carry on the flow chart. So moving from box 3, we've got two options. You can either become symptomatic because you've become infected, or you might remain asymptomatic. So again, we've got two destination boxes or two transit boxes. Box 4 is where you're going if you're symptomatic. Box 13 is where you go if you're not symptomatic. And again, we've got two attached probabilities, and because it's exclusive, you're either symptomatic or you're not, the sum of the two probabilities must again be 1. So you can imagine someone's coming along the blue sign of boxes. They're transit boxes in the sense that once you start in box 1, you don't necessarily stay there. You can move to box 2, and you don't stay in box 2, you become either box 3 or box 12. And if you're in box 3, you don't stay there, you become either box 4 or box 13. But when you're in the green boxes, you'll tend to stay there, although I've got a caveat for that at the end of the chart. From box 4, symptomatic, we've actually got 3 destinations, because you might, if you're symptomatic, let's go downwards first, you might end up in box 14, which means you just recover. You were symptomatic, but you recovered. You didn't need to go to hospital. Might be mild symptoms, moderate symptoms, might be quite severe symptoms, but you stayed in bed, stayed at home, and you recovered. You might equally have been hospitalized. So your symptoms might be sufficiently acute that you end up in, or you're traveling to box 5 and you're COVID and hospitalized. And there is a chance, and I think there's quite a lot of evidence within the data that there are routes where you are symptomatic, but acutely and severely symptomatic, and eventually die with COVID, but you didn't actually go into hospital. That might well be because you're in a care home, you died in a care home of COVID. There is some evidence because deaths at home is increasing as a weekly statistic. Maybe there are cases where people are severely ill, they don't want to go into hospital because they think they're going to get COVID, even they've already got COVID, and they pass away at home. So you could end up in box 7, because obviously death is very definitely an endpoint. That is a green box, and you could end up in box 7. But from box 4, we've got 3, box 7, box 5, and box 14. So now the sum of those 3 probabilities has to equal 1, because you're in one of those routes from box 4. From box 5, we've got 2 possible outcomes. You're in hospital. Within hospital, there's various sub-processes. You might end up in critical care or whatever. But if I simplify that, you're either going to die in hospital or you're going to be recovered. And eventually, obviously, when you've recovered, you will leave hospital. But again, I've got 2 end boxes. The sums of those 2 probabilities has to equal 1. So if you're in hospital, you'll either die or you'll recover. So one of those 2. You'll notice I've left a space here, and that's because it occurred to me, and this is quite relevant, that naturally, as part of the process of being a human being, some of us end up in hospital. We break a leg, we have renal failure, we have a heart attack, whatever it might be, we end up in hospital. And that, although there's evidence that a lot of those things are reducing because people are avoiding going to hospital, that will still be happening. So although I describe these green boxes as endpoints, particularly these here, 11, 12, 13, and 14, actually that's not quite the case, because some of them will lead to hospitalizations. I've added quite a lot of detail in one go there. So some fraction of those people that were in each of these green boxes will go into hospital for what I'd call non-COVID hospitalization. So you've broken your leg, you've had a heart attack, whatever it might be, you've gone into hospital because of that. So you could arrive in box 15 from each of these boxes. And then from box 15, you've got 2 choices, if you like. You can recover or you can die. I've done a separate hospital death in the sense that box 17 are non-COVID hospitalized deaths, and box 6 are COVID hospitalized deaths. And then I've got them both going into the same recovered box. Maybe in another model might split those out, but you could recover in hospital, and you may have had COVID, you may not have had COVID, but equally you could die from not having had COVID but going into hospital. Now that's my little flowchart model, and what really interests me, and this is what really sparked it. Can you see I've drawn this dotted line, this dotted box around the 2 hospitalized boxes? Here in the UK, most of the PCR testing so far has been at point of entry into the hospital. And I know the data is a few days old, but they're numbers that work quite well for describing. At some point last week, a total of 500,000 tests have been carried out. 125,000 of those have tested positive, so therefore 375,000 hadn't. So that gives us a handle on the numbers in these 2 boxes. Box 5 are entered hospital with COVID, box 15 entered hospital without. I've drawn a faded arrow between the 2 boxes because, and this is something in the era of superbugs, when way out of COVID, just in normal hospital situations, when hospitals have norovirus or something like that, then you might go into hospital with a broken leg and contract norovirus when you're there. So there is going to be some, I am sure, people who enter hospital for non-COVID reasons and without COVID, but actually they become COVID positive whilst they're in hospital. There is also the issue that although 500,000 tests have been carried out, some of those could be multiple on the same person. So it doesn't mean 500,000 patients have been tested 500,000 times the test has been used. Now, let's go back to those numbers I said. 125,000 confirmed positive PCR tests in the hospital system, therefore 375,000 negative tests because there were 500,000 tests in total. So that gives you a ratio between, in the hospital situation, how many people entering the hospital system are positive versus how many are negative, or putting another way, of the percentage of all those entering the hospital system, what percentage of all those entering, what percentage are COVID positive and what percentage are not COVID positive. Now, what I've seen is people using that ratio of COVID positive, COVID negative entering the hospital system to extrapolate back to an estimate of the total population of the country that have been infected with the virus. Now, let me show you why I don't think that is the right thing to do. Let me go back to the flowchart and what's interesting about the flowchart. And I've moved my cursor to box 3, just an example. If I know how many people are in box 3, and I know how many people are in box 4, I've got an estimate of this ratio P symptom. So for example, if there are 100 people became infected and 50 of those became symptomatic, I know that the probability of becoming symptomatic is a half, because I started with 100 in box 3, 50 ended up in box 4, therefore my ratio between the two boxes is 0.5. Equally, if that ratio had been 0.3 and I started with 100 in box 3, then 33 1/3 would be in box 4. So these ratios between the arrows are also equivalent to what you multiply. If you know the total in one box, what you have to multiply that total by to get an estimate of what's in the next box. So for example, if I wanted to go from box 3 to box 5, I would need to know the number of people in box 3 and the two ratios, the probability of becoming symptomatic if you're infected, and then the probability once you're symptomatic you need hospitalizing. But if I do know those two ratios, and I know the number of people in this box, I can estimate how many are in here, box 5 rather. Putting it the other way, if I know the number of people in box 5, and I know the ratio, the probability of being hospitalized if you're symptomatic, I can, by effectively a process of division, I can go backwards. So for example, I know that for every 100 people that are symptomatic, 20 end up in hospital. So 100 there in box 4, 20 in box 5. That 100 to 20, that's a fifth. So then if I multiply the number of people in box 5 by 5, I get back to how many were in box 4. So I've got this ability to estimate numbers between the boxes. Let me put some numbers on the boxes to explain why I think this ratio that's been used between total tests and the number of positive tests is the wrong ratio to use. So let's imagine we started with a population of 1,000 people. And let's say 500 of those were exposed and 500 weren't. So that's 50-50. So that means I've estimated those two probabilities as 0.5 each. Remember, they have to add up to 1. Then those 500 in box 2, 200 of them go to box 3, 300 of them go to box 12. So that means I've estimated probability infected at 200 out of 500, which is 0.4, and therefore this must be 0.6 because those two have to add up to 1. The 200 that end in the infected box, or arrive in the infected box rather, let me say 50, a quarter of them become symptomatic, 3/4 don't. These I'm not necessarily using ratios I've seen from data, I'm just using something to make the numbers on the chart fairly straightforward. So that's 1/4 get me to the 50 in box 4, 3/4 gets me to the 150 in box 13. From box 4, I've got 3 exit points, and I've decided 2 for my numbers, 2 end up dying, 5 go into hospital, and 43, therefore, to make up the 50, are symptomatic, not hospitalized, and recover. Okay, and then the 5 that end up hospitalized, I've assumed 2 die and 3 recover. So that's my 5 there. So that's my sort of putting some numbers. So I've got some numbers to work with. What I then also described was this idea, well, actually, just as part of normal life, people end up in hospital. So of these 500, 300, 150, 43, I'm going to say some of them disappear, but move into the non-COVID hospitalized box. So of my 500, 493 stay in the so far unexposed total and not in hospital, but that means 7 of those go into this box 15. 300 versus 295, that means 5 of those from box 12 have moved over into box 15. 150 to 148, 2 of those moved into box 15, and 43 versus 2 is one of those. So in total, I've got 15 that have gone into hospital, not because they had COVID, because they've broken their legs, they've had heart failure, whatever it might be, that were the non-COVID reasons. And then of those 15, let's say one of them dies, that's the 1 plus 3, they're making 4 in total, and 14 of them recover. So I've put some numbers on the boxes. And I've deliberately chosen those numbers because the ratio, so when they do the PCR testing of people arriving in hospital, we've got PCR positives and PCR negatives. And the ratio is, as I've shown here. So 125,000, these figures from a few days ago was the total positives. 500,000 was the total number of tests. So therefore, 375,000 are the negatives, but that's the same ratio that I've got here. So basically, a quarter of all those people in hospital, 5 out of 20, a quarter of all those people in hospital were PCR positive. And then what I've seen people do is use that 1/4 to come over to box 1, the population, and say 1/4 of the population are infected. So if I was doing that, that would be 250. But can you see that's not right? Because if you remember, to get from between two boxes in my diagram, you have to use the probability to get between, I'll go a 3-stage or a 2-stage journey from saying here from box 1 to box 3, I have to multiply those two ratios together. But that's not the ratios I've got. I've got the ratio of positive test to negative. It's not even this arrow here. This is the leakage between the two blue boxes, rather than the thing that explains the ratio between them. But I've used that ratio in there, so in this dotted rectangular box, all the hospitalized cases, to then apply as if I'm doing this journey from box 1 to box 3. The only way I can do the journey from box 1 to box 3 is by knowing these two combined ratios, probability exposed and the probability infected. Now, the sampling you can do to estimate that, and I'll perhaps do a different video showing you which boxes we need to sample from to give us that ratio. But what is clear is that the ratio within there, where my arrow is here inside that dotted box, is not the ratio that should be applied to box 1. And I say in the example here, because they're using the ratio of approximately a quarter of all tests are proving positive, they are then applying that ratio of a quarter to the number infected. Okay, it's close from these numbers here, but that doesn't mean it's going to be close with the real numbers. It's just the numbers. So 250 is what you'd estimate if you applied that ratio on this dotted arrow here, where actually 200 was the number from the numbers I put into the model. Another example I want to give you of perhaps where the wrong ratios have been used was something from The Guardian a few weeks ago, where the author of a particular article looked at the number of positive PCR tests entering the hospital system. So again, my number of 125,000. At the time, it was less than that. So this must have been 10 days, 2 weeks ago or so. But I'll stick with my figures of 125,000. He was looking at that, but then he used another statistic, which was from a study in China. The study in China had shown that 80% of infection cases were asymptomatic. So let's be quite clear on my diagram which probability that's talking about. That is actually the arrow that connects box 3 and box 13. So the probability of being infected but not symptomatic was 0.8. So 0.8 is the ratio that gets us from box 3 to box 13, which means, if you remember, because there's only 2 boxes coming out of box 3, that the sum of this probability I'm circling with the cursor here and this one here has to be 1. If we know this one's 0.8, the one from the paper in China, then this one connecting box 3 and box 4 is 0.2. Remember, if it's 0.2 is the multiplication factor going from box 3 to box 4, it's the division factor going from box 4 back to box 3. Now, what he did in this article in The Guardian is, if I can get this to move on, oh, no, it's not going on, is, there we go, that's what I need to do. What he did in this article was he took the number of tests, which is box 5, and then used that divisional factor of 0.2 to move us back to box 3. But I've just shown you the 0.2 is in fact only the arrow between box 4 and box 3. He ignored this arrow between box 5 and box 4. Now, what this arrow here is, and you'll understand this if I put this in sort of English rather than symbols, is that not every case that is symptomatic requires hospitalization. The Chinese paper study was looking at being asymptomatic versus being symptomatic. He wasn't looking at being asymptomatic versus going into hospital. So there's a key part of the chain. What's the probability that if you are symptomatic, those symptoms are sufficiently severe that you end up being hospitalized versus you're symptomatic and they're quite severe, but you still don't be hospitalized. So to emphasize the point, he was applying a ratio that should have been applied to get us from box 4 to box 3 to get us from box 5 to box 3. So his ratio, his estimate would have been wrong. So I think this is why this flowchart model is quite useful, because it allows you, when you're taking data, you can visualize which box the data is coming from and which probabilities you need to know to move you from one box to another. So if you're doing some estimating, you know which probabilities you need to know, or if you know the numbers in two adjacent boxes, then you've got an estimate of the probabilities between them. So that's the model. Let me know what you think. I'll probably be using it to look at some sampling a little bit later in terms of if we do antibody testing, from which of the green boxes should we be doing the antibody testing and what it would mean depending from which box we are taking those samples. So let me know what you think, and I'll probably be back with another video with this same flowchart.